The largest things in the universe are black holes. In contrast to things like planets or stars, they have no physical size limit and can literally grow endlessly. Although in reality, specific things need to happen to create different kinds of black holes, from really tiny ones to the largest single things in the universe. So how do black holes grow? And how large is the largest of them all? This video will not discuss how black holes work or how they form, since we've looked at that in detail in our black hole and neutron star series. You can check them out afterwards. For now, we're interested in finding the largest thing in the universe. Let's start really small. Primordial black holes. The smallest kind of black holes may or may not exist. If they do, they're probably the oldest objects in the universe, older even than atoms. They would have formed just after the Big Bang, when the universe was so dense with violent energy that any tiny pocket that was just slightly more dense than its neighbors could produce a black hole. The smallest primordial black hole that could still be around would be 8 trillion kilograms or so, the mass of a big mountain. And yet they would be no bigger than a proton. A primordial black hole with the mass of Earth would barely be larger than a coin. This makes them very hard to find, so we haven't actually observed any yet. If they exist, they may even be the mysterious dark matter that holds galaxies together. Let's move on to the kinds of black holes that we know for sure are out there. Stellar black holes. To make a black hole, we need to compress enough matter so that it collapses into itself. After that, the more mass we throw at it, the larger it becomes. In today's universe, only the most violent cosmic events can create the necessary conditions, such as the merger of neutron stars or when the core of a very massive star collapses in a supernova. To have a unit to work with here, we'll use the mass of our Sun, about 2 million trillion kilograms. The smallest known black hole has 2.7 times the mass of the Sun, which works out as a sphere around 16 kilometers in diameter, large enough to cover Paris. Another lightweight black hole is the companion to the V723 MON red giant star. This star is 24 times larger than our Sun, 30 million kilometers in diameter. And yet, it's thrown around by a tiny black hole just 17.2 kilometers wide. This tiny thing bullying the star is so much smaller that we can barely even show them in comparison. One of the largest known stellar black holes is M33X7. It currently spends its time eating a 70 solar mass blue giant bit by bit. As all that stolen matter circles towards the black hole, like water going down a drain, friction heats it up to temperatures high enough to shine 500,000 times brighter than our Sun. And yet, X7 is only 15.65 solar masses and 92 kilometers wide, just big enough to cast a shadow on Corsica. To grow much larger, black holes have to either devour a lot of stars or, better, merge with one another. The instruments that make it possible to detect these mergers are very new, so we're currently discovering a lot of exciting things. Like 2 massive black holes that we detected in a galaxy 17 billion light-years away. As they spun around each other violently, they released more energy in the form of gravitational waves than the combined light from all the stars in the Milky Way in 4,400 years. The new black hole they formed is about the size of Germany and is 142 solar masses. And here we hit a curious gap in scale. There are lots of black holes up to 150 solar masses, and then there's nothing for a long time. Until we suddenly hit black holes that are millions of times more massive. Which is a bit confusing because we had this idea that black holes are consistently growing and growing. But for the most massive black holes, this process is not fast enough to explain their existence today. The universe is simply not old enough for these supermassive black holes to have formed by eating stars and merging with each other. Something else must have happened. To explain how we got the largest black holes in the universe, we might need the largest stars that ever existed, quasi-stars. To get a sense of scale, we can compare them to the largest stars that exist today. Our Sun is like a grain of sand next to them. We don't know if quasi-stars actually existed but they're an interesting concept when it comes to supercharging black hole development. The idea is that the matter in the early universe was so dense that quasi-stars could grow to thousands of times the mass of our Sun. The cores of these stars might have been crushed by their own weight so much to actually collapse into black holes while the star was still forming. In contrast to stars today that would destroy themselves in the process, inside quasi-stars, a deadly balance could emerge. Gravity pressed the supermassive star together, feeding the black hole and heating the material falling in to such a degree that the radiation pressure kept the star stable. And so these quickly growing black holes might have been able to consume the quasi-star for millions of years and grow far bigger than any modern stellar black hole. Black holes several thousand times the mass of the Sun and wider than the entire Earth. These black holes might have become the seeds for supermassive black holes. So now we arrive at the kings of our universe, the largest single bodies in existence. The centers of most galaxies contain a supermassive black hole, and they are monstrous. In the Milky Way, we have Sagittarius A star, a supermassive black hole with about 4 million solar masses that is calm and collected and just does its thing. We know it sits there because we can see a number of stars being thrown around by a seemingly empty spot. And despite its incredible mass, its radius is still only 17 times our Sun. Smaller than most giant stars, but millions of times more massive. Because supermassive black holes are so massive and located at the center of galaxies, many people imagine them as being a bit like the Sun in the solar system. An anchor that glues everything else together and forces it into an orbit. But this is a misconception. While the Sun makes up 99.86% of all the mass in the solar system, supermassive black holes usually only have 0.001% of the mass of their galaxy. The billions of stars in galaxies are not gravitationally bound to them. Instead, it's the gravitational effect of dark matter which holds them together. Many supermassive black holes aren't gentle giants, especially when they're feeding on the clouds of mass in their galaxy. The one at the center of the BL Lacerti galaxy is devouring so much material that it produces jets of plasma accelerated to nearly the speed of light. If Earth were orbiting this huge body, it would seem 115 times larger than our Sun in the sky, and we'd be burnt to a crisp in seconds by its glowing hot accretion disk. At this point, black holes become so large that stars seem ridiculously tiny compared to them. The galaxy Cygnus A has a supermassive black hole with 2.5 billion solar masses and 14.7 billion kilometers wide, which would mean that if it took the place of our Sun, it would swallow all the planets and stretch halfway to the edge of our solar system. It's devouring so much mass and material that it churns its disk into a kind of magnetic funnel, spewing gas out, making tremendous radio lobes towering over the galaxy 500,000 light-years in diameter. That's 2.5 Milky Ways wide. Another pretty large supermassive black hole sits in the galaxy Messier 87. It has 6.5 billion solar masses and was the first black hole we got an actual photo of, or rather of the glowing gas around the edge of a menacing shadow. This sphere of darkness is so large that it covers our entire solar system. And yet, there is a scale even above these kinds of objects. Ultramassive black holes. Now we reach the most massive black holes, perhaps the largest single bodies that will ever exist. These black holes have eaten so much that they've grown to tens of billions of solar masses, their gravity the engine for a quasar, an accretion disk shining brighter than thousands of galaxies full of stars. So massive that they deserve a title of their own: ultramassive black holes. The ultramassive black hole at the center of galaxy OJ287 is 18 billion solar masses. It's so big that it has a supermassive black hole nearly 40 times larger than Sagittarius A star orbiting it. This thing defies imagination and is really hard to compare to anything. It can comfortably fit 3 solar systems side by side inside of it. Let's end this insane competition and get to the King of Kings, TON 618, a black hole that we can observe consuming galaxies worth of matter, is shining with the brightness of 100 trillion stars, visible from 18 billion light-years away. It has an incredible 66 billion solar masses, a black hole so large that it would take light a week to reach the singularity after crossing the event horizon. About 11 solar systems could sit inside of it, side by side. It may very well be the largest single body in the universe, but in reality, it's probably even larger. Since TON 618 is so far away, we only see what it looked like 10 billion years ago. In any case, black holes are scary and mysterious and gigantic. They'll be here after everything else dies and growing larger and larger. Okay, now let's do the trip again. From the smallest possible black hole all the way up to the largest. Let's try something new today. We can call it Behind the Lies, a short behind-the-scenes bit about the necessary inaccuracies in this video, because it's not really actually possible to rank black holes like trading cards. How so? Well, while we've catalogued millions of stars, we really only have good data on a couple of dozen black holes. That's because black hole gazing wasn't really a thing until 50 years ago, and technically still isn't because we can't see black holes. We can only derive their properties from studying their gravitational effects on the matter around them, like the orbit of stars that come close to them. This effect depends on the mass of the black hole, which we can approximate at the most basic level with Kepler's laws. But this comes with huge uncertainties and error bars. Then we have to convert mass to size next, which brings new uncertainties. For example, we calculated the radius from the mass using the Schwarzschild equation, which for the sake of simplicity assumes black holes are perfectly round and don't spin, a kind of black hole that doesn't really exist. The reality is that physics on these scales is a bit fuzzy. So some of the black holes we talked about here may be way smaller or way bigger. We just don't know for sure. We shimmied around this problem by comparing different sources with different kinds of values and using different mass calculations to arrive at a standardized list that allowed us to be as accurate as humanly possible. You can look at all of this in our source doc. As a result, this script was written with the tears of experts we drove crazy with our obsession for the best values they could live with. In this process, tons of stuff got cut and didn't make it into the final video. But luckily, we found a way to not waste all of it. We've created a lot of black hole merch, spanning the whole range from somewhat bonkers to more serious. This way, we get to explore a topic from different angles, and you get to continue having fun with black holes after this video ends.